So good Corona time to you, and hopefully you're doing well. Today I want to talk about the standard template library, and the title of today's talk is What You Absolutely Positively Need to Know About the Standard Template Library, featuring Smiley and the Microsoft Clipart team. So this is chapter 21 in the D.S. Malik book. And what is the standard template library? Well, it's a large collection of standard data structures for holding data, and it includes libraries for these data structures. Stack, queue, vectors, and more, and linked lists. And these are called container classes, but there's more to it. There's a collection of libraries written in the standard C++ language. There's also algorithms and iterators to move through those. So the standard template library is not a part of the core language, but it is part of the standard implementation, so it's generally available on most compilers, unless you're using some strange C++ compiler, in which case you're kind of on your own. And the classes in the standard template library are templates. So that's why we covered templates earlier in the semester. So it also has iterators, which are constructs that facilitate cycling through the data. You may remember using pointers as iterators to move through a linked list. If you watched the previous linked list presentation, iterator is equal to iterator here, follow the link. So it also has implementations of many generic algorithms such as searching and sorting, and these are implemented as template functions. So again, that's why we covered templates in these algorithms a bit early on before introducing you to this, so that you would know what those were, how they operate, and how you can actually use them. And now that you have the standard template library at your disposal, it'll be a lot easier for you to use them. So it has containers, algorithms, and iterators. The containers hold objects. They're all of a specified type because they're a template class. Generic algorithms that act on objects in the containers, and iterators that are used to step through the elements of the container. And Smiley says, gosh, I'm going to be sick after doing everything the hard way throughout 150 and 151. But there is a reason we introduce this later in the course, and it's so you have the background to be able to use it properly. So iterators are the tools that we use to get through the containers. And it's a generalization of a pointer. We can skip on the details of implementation, but think of it as a pointer that can advance through the data structure. Each class is going to have its own iterator types, but all iterators behave similarly. And there are a couple different classes that we'll go through so that you can see the different classes of iterators. So what are some operations shared by all iterator types? One is plus plus, that advances to the next data item in the container. Equal, equal, and not equal to test whether two iterators point at the same data item. A dereferencing operator that provides data item access. Begin, that returns an iterator pointing to the first element of the container. End, that returns an iterator pointing just past the last element of the container, so you can go all the way to end and catch the last item. So you can use begin and end to cycle through a container using a for loop and process the items. There's also reverse begin and reverse end if you want to do things in reverse order. So basic iterator operations, again, minus minus, if you have a bidirectional, moves to the previous item, and it's available for some kinds of iterators, bidirectional ones. Star P access can be read or write only, depending on the container and the definition of the iterator. And STL containers define iterator types appropriate to the container internal. So the iterator for a list is going to be somewhat different than the iterator for a vector. Some containers also provide read-only iterators. So speaking of vectors, we discussed those and we've used them in some of our programs. They act like an array, but they can grow and shrink in size. And there are some differences. For example, how we declare it, because vector is a template class, we need to indicate the underlying type, in this case vector int, and give it a name sample. And then initialization, we use the push back command, which adds an element to the next available position. We can also get the size, doing sample.size in order to step through using a for loop, and we use it just like an array in terms of getting access using the square brackets. The other thing that's important is we need pound include vector. you can have iterators with vectors instead of using those for loops. And here you need a using directive. It's different from the previous using directives in that you use the scope resolution operator, that's the 2 colons, and identify the iterator as a type. So here we would say using standard : vector int, which is the under the vector and its underlined type, : iterator. And within the scope, you can now have an iterator P. You indicate standard because you might have another namespace with vector. Just, for now, work with it and don't question it too much. 3 types of iterators: forward, ++ works on this; bidirectional, both ++ and -- work on the iterator; and random access iterators, which ++, --- and naming specific elements as in sample2 work. Vectors are a type of vectors have a random access iterator included in them. Constant iterators have dereferencing operators to produce a read-only version of the element, so you can't modify them. And mutable ones allow you to change the values. There are also reverse iterators that allow you to step through the elements in the container in reverse order. So what are these different types of containers? Well, we've already seen vector, but different types of containers are used for holding data: lists, queues, and stacks, which we've seen in our previous 3 presentation. And each one is a template class with the parameter for the type of data to be stored. For example, a list of doubles, a queue of Boolean values. All of them have iterators, all have member functions for begin and end. And each one has special functions to add or delete data. So the sequential containers means the container has the first element, a second element, and so on. The sequential containers are list, vector, and deck, which is a double-ended queue. An STL list is a doubly linked list. So that means you can go forward and backward with it. STL vector is essentially an array whose allocated space can grow while the program runs. And an STL deck, or DQ, is a double-ended queue. Data can be added or removed at either end, and the size can change while the program runs. So it gives you a bit more flexibility over the traditional queue. Common members, Malik provides a list of common member functions for all containers. The sequential containers each have different characteristics, but all of them support these member operations: constructor, a destructor, a function empty that returns true if there are no entries, size, and an assignment operator. So you can see there you don't actually have to define the big 3 for these, even though they use dynamic memory. Somebody's already gone in and done that for you. So that's a nice feature, if you recall back to some of the problems we had with implementing the big 3. Swaps the contents of one container with another. Push back appends an item to the container C. Begin and end return iterators to the first element and an iterator to a position beyond the end of the container. RBegin is reverse begin. It returns an iterator to the last element in the container, and you can use this for reverse reversal of the container. And RN returns an iterator to a position just before the front of the container. So again, that's part of the going through the container in reverse order. Front and back. Front returns the first element of the container, and back returns the last element of the container. And you can do these in a different way, but I think front and back are probably easy. Inserts a copy of an element before the iterator. Erase removes an element an iterator points to, returns an iterator to the element following erasure, and returns c.end if the last element was removed. Clear. That one makes the container empty, and that's a handy one to use for resetting the container. You can also compare for equality with double equal and not equal, and then push front, which will insert an item at the front of the container. It's not implemented for vector due to large runtime results. Beyond the sequential containers are adapter containers, and these are classes that are implemented on top of other classes. So a couple of these are stack, priority, queue, and the priority queue behaves like a queue, but each member has a priority, and higher priority members are removed first. So you can think of a priority queue as being the boarding area for Hawaiian Airlines. They welcome the Pualani Gold and Platinum members, followed by customers traveling with small children, and followed by the Zone 3 and then Zone 4. So that's an example of a priority queue. You can specify an underlying container instead of the default, which is deck. Just make sure you use the space between the arrows. So I can make a stack of integers with vector as its underlying container instead of the deck. And that might be a more natural way to go about it. So associative containers, these act like pretty simple databases. And this is the third type of container. There's set, which stores elements without repetition. That's nice because you can keep inserting things, but it won't repeat. Each element is its own key, and you can ask whether something is in the set or not. A map is a function given as a set of ordered pairs. Basically, you could use it to map a number to a string. So I can do map string int, number map, and then here the strings are the key. So each string will return a unique number. Some of the set operations includes returns true if every element in the first range also occurs in the second range. Set union, intersection, and set difference that you learned in CS 141, CS 241. You can actually implement those. And so here's a summary of the containers. So there are sequence containers, which are vector, deck, and list. Associative containers, map, multi-map, set, multi-set, and the adapter containers, stack, queue, and priority queue. And it gives you the type of iterator support and the associated header file. The other thing included in the standard template library is a set of generic algorithms. And some of you have used the sort from this before, so it should be pretty familiar. There are also function templates, and they are template functions that use iterators as template parameters. So in order to use these, you need to have pound include algorithm, and you also need to know the type of arguments to give them. The algorithms themselves are classed into non-modifying sequence algorithms, modifying sequence algorithms, sorting and related algorithms, and numeric algorithms. So let's take a look at each type. Non-modifying ones basically don't modify the container that they operate on. They don't change anything. So for example, here is the function find. So find needs us to give it an iterator to the first element where we're looking, an iterator to the last element where we're looking, and the value that we're looking for. So it also tells us that find works with any container that provides an iterator at least as strong as an input iterator. And type T objects need to be comparable for equality. So you need to be able to say that one is equal to the other. So if you're using it with a class that you built, you need to define double equal by overloading the operator. Other non-modifying ones, count, counts the occurrences of a value in a sequence. Equal asks if are the elements in two ranges equal. Search looks for the first occurrence of a match sequence within another sequence, and binary search searches for a value in a container using less than. If the container was sorted using another predicate, this predicate must be supplied to binary search. This is an efficient search compared to sequential search. Container modifying algorithms change the elements within the container. So copies from a source range to destination range, and that of course modifies the container. This can be used to shift elements in the container to the left, provided the first element in the source range is not contained in the destination range. Remove removes all the elements from a range equal to a given value. And, it's handy for taking out non-answers in a survey or any type of other element you might want to remove, such as zeros or negative numbers. Reverses the order of the elements in a range, and then there's shuffle or random shuffle. Depending on which version you're using. Shuffle is the newer version, and it shuffles the elements of the sequence. Argument 1 in this case is an iterator pointing to the first element in the sequence, and argument 2 points one position past the last element to be shuffled. The numeric functions, accumulate finds the sum of all the elements in a given range. Adjacent differences creates a sequence in which the first element is the same and all other elements are a difference of the current and previous elements. So That one's handy for programming team problems. Inner product multiplies corresponding elements of two ranges. That's handy if you want to emulate vectors from mathematics. Partial sum creates a sequence in which each element is the sum of all previous elements in the range. So you can keep a running partial sum, and that's kind of a cool feature of it as well. Sorting algorithms. All those STL sorting algorithms are required to be O of n log n, so the algorithms are as fast as possible. In practice, they use a mix of different types of sorts. So sorts the elements in the range in non-descending order or in an order determined by a user-specified binary predicate. Merge merges two sorted ranges into a single destination range. For C++ 11 and up, there are some new items. Shuffle, is permutation, is partitioned, is sorted, and min-max. And you can go to C++ reference and look at those updated new items that Malik didn't cover. Next time we'll explore some of the standard template library in more detail with a couple different labs, and keep this one a secret so that the CS150 students don't find out about it and don't use this stuff before they're capable of using it. Thanks so much for listening, and as always, you don't have to like, share, or subscribe, but I appreciate you taking time to learn C++.